Am I crazy? Or why doesn't someone just make a P2P version of an LLM? The more seeders, the stronger it gets, beating all of the paid offerings. This was a sentiment I held, and honestly, after I started digging deeper into LLMs, it became obvious why this would not work. And in fact, it's in my reply as well. Network latency. The main problem is that when we think of a P2P network, what we're imagining is something like BitTorrent. And the way BitTorrent works is completely different from how LLMs work. With BitTorrent, you have one computer that wants to get some information, and it's going to talk to multiple computers on the internet to get that information. Let's say we want to download a file using the BitTorrent protocol. This is obviously an oversimplification, but what would happen is that computer 1 would request computer 2 to send, say, the first third of the file. It would ask computer 3 to send the next third, and the computer 4 to send the last third of the file. As a result, this is extremely parallelizable, and you can request different things from different computers. This will improve speed as well as download performance, and it does not overburden any single computer or server. However, this doesn't work the same way with LLMs for one reason. They're not that parallel. So the main way LLMs work is that they have a bunch of these layers which are made of attention blocks and MLP blocks, and all of them are stacked one after the other, and modern large language models have almost 30 to 50 or even more of these layers laid one after the other. As a consequence, before any layer can start doing its math, it needs to make sure that the previous layer has done its math. If not, then the current layer cannot do its thing. As such, this is a sequential process. Now, some of us may think, why can't we pipeline this? So why can't this layer start doing its math before this layer is done? Unfortunately, it doesn't work that way because the inputs to this layer are the outputs of this layer. And until we have all the outputs, we cannot start working on this layer's math. Another thing about LLMs is that each token has to be generated one at a time. So if we say that we have one full flow through this LLM to generate one token, then to generate the second token, we need the output of the first token from this end before we can feed it back as an input to the LLM to generate the next token. This is just a result of LLMs being auto-regressive by nature. And by that, I mean that every token depends on all tokens that have come before it to be generated. Both of these things render LLMs, and particularly the decode step where they're generating tokens, to be extremely sequential and not parallelizable. As such, even if you did have different machines to do each of this math, then they're all going to be constrained by waiting for these outputs to come through. And consequent speed at which they can be moved between the different machines is what is going to affect the ultimate system performance. Now, in real data centers, where you have these humongous models that need to run on GPUs with about 80 gigs of VRAM, you have NVIDIA's NVLink, which offers a bandwidth of several hundreds of gigabits per second, so you can actually move these outputs between layers pretty fast. But when you're trying to run this on, say, your home network or across the internet, then you're constrained by Wi-Fi speeds, which 10 gigabits per second itself is extremely nice, but usually you're in the megabits per second range. So right there, you have almost a 1000x difference in bandwidth, and that's just going to constrain how fast your model can generate tokens. So let's actually look at what this would look like in real life. So if we have, say, a master machine, which is going to handle all the model, and then it's going to say machine 1 is going to run, say, the first 10 layers of the LLM, machine 2 will run the next 10, and machine 3 will run 20 layers of the LLM. How you shard the model completely depends on the algorithm that you're using. So we're not going to get into that. Instead, let's see how this would work in real life. We have the master machine that says, okay, machine 1, you have to start generating tokens. We're going to wait for machine 1 to do all of its math, which should be fast enough. And then we have to wait for a slow Wi-Fi connection to move the weights from machine 1 to machine 2. Once machine 2 has the inputs, it can start working on its math, and then it'll send its outputs to machine 3. So as you can see, the math within each machine will not take too long, but only one machine can work at a time unless we implement more aggressive speculative strategies for decoding. So when machine 2 is working, only it can work on decoding the weights, while machine 3 has to wait for the outputs of machine 2, and machine 1 has to wait until this entire generation run is over. Now, this is all good in theory, but let me also show you a demo so that you understand why this is extremely infeasible with the current architecture of large language models. Here, I have a demo setup, and we're going to be using llama.cpp for this. Llama.cpp has this feature where you can actually shard models and run them on different computers. However, since I have only one computer, I will be simulating this by running the different processes which would run on different machines, ideally, on my own machine. They'll just be exposed on different ports, and we're going to have one master process that manages all of this. But before we get into that, let's just see how this model runs without any of this sharding. I've picked LFM's 1.2 billion parameter model that they released last week for this demo. So I'm just going to ask you to write a short story about a robot cluster working together. It's going to take a moment to load the model. Now notice that loading the model took very little time, and generation was about 20 tokens per second, which is pretty fast. Next, we're going to shard the model. I'm going to simulate this by having 3 processes running, which will act as the worker machines. So I'll expose one on port 50,052, another on port 50,053, and third one on port 50,054. Then we'll use llama.cpp's capabilities to connect these models together, and we will use the RPC mode to treat this as a sharded model and run it across the different processes. I will use the same prompt using the same model and the same number of tokens to be generated. And let's see how long it takes. Instantly, you'll notice that loading the model takes much longer than before. And if you're looking at the generation speed, you would say that it wasn't really effective. With regards to model loading, the reason it takes longer is because you need to now load it across different machines and coordinate between them, and that is inherently slower than just loading all the weights into one process. Second, the generation speed did not take a big hit compared to the non-sharded version, and that reason is because I haven't really introduced any network delays. So let's add that and see how slow this gets. I'm going to use a built-in utility called traffic controller in Linux. So what I'm going to do now is add a delay of 25 milliseconds for each packet that is sent and received. To see this delay in action, let's look at the ping command. I'm trying to ping localhost, and this should be extremely fast because it's my own computer, but you can see that the round trip time is 50 milliseconds. That's because there's a 25 millisecond for the request being sent and a 25 millisecond delay for the request being received. This is a reasonable approximation for delays in Wi-Fi. Now, with this delay, let's see how long it takes for the model to generate the story. You can already see that it's going much slower than before. It's going to take a little longer to get this done, and based on my previous experiments, it's about a 5 to 10x decrease. As you can see, the generation speed is 3.3 tokens per second, which is 6 times slower than the non-sharded version. Now, 3.3 tokens per second is extremely slow. Honestly, it's slower than reading speed, and as such, it's probably impractical to rely on this for hosting big models. Now, unless you're trying to do a test or you're okay with a model taking this long to generate things, you should ideally stay away from peer-to-peer LLMs. And also note that this 3.3 tokens per second is while running a 1.2 billion parameter model. If you try to run a 70 billion llama model or a 405 billion parameter llama model, that's probably going to be another 10 to 100 times slower. So it'll probably take you a solid 10 to 15 seconds just to generate one token. And that is assuming that you have all the compute necessary. So this is why, unless we get a better model architecture, which is more parallelizable, we're unlikely to see peer-to-peer networks take off for running large language models locally. I hope this was informative, and I'll see you all the next time I want to talk about something cool.